Chapter 3. The Problem with Renewables. Wind and solar are the basic forms of renewable energy. In some parts of the world, hydropower can be further exploited. This may be possible in Norway, for instance. For the rest of Europe, as has been demonstrated over the past 20 years, wind and solar are widely available. Both have collapsed in price and now come in at a fraction of the cost of nuclear, coal, or gas-fired generation. Solar uses the photoelectric effect, discovered by Albert Einstein, and for which he was awarded the Nobel Prize. It directly converts radiation from the sun into electricity. When we installed the first wind farm in Ireland in 1992, the size of the turbines was 0.25 megawatts. Single offshore turbines today can produce 16 megawatts at full output, a factor of 60 times bigger than the early 90s variety. The cost of a wind turbine is directly related to the length of the blades, R. The energy that the blading system captures is related to the circle traced out by the blades, PR. This explains why turbines continue to get bigger. For an increment of length of blade, and therefore cost, the energy captured is proportional to the square of the blade length. There are two great differences between fossils and renewable energy. One is the concentrated nature of energy locked up in fossil fuel molecules. The second is the transportability of fossils. Coal, oil, and gas can be shipped to where they are burned, whereas wind and solar cannot. Wind and solar must be harvested where they are at their strongest. The energy in the wind and the sun is turned into electricity and must be transported as electricity to where it will be consumed. It would be possible to further process the electricity, using it to crack water, for instance, to manufacture hydrogen. Up to 40% of the energy in the electricity is lost in this process. The majority of the cost of turning water into hydrogen, perhaps as much as 70%, is the electricity cost. For cost reasons, hydrogen may be manufactured where cheap solar is abundantly available. Is solar not enough? Skeptics could argue that we should forget about wind energy and concentrate on solar PV. Solar is cheap, the cheapest form of electricity generation in history, according to the IEA, and right now does not appear to need the kind of assistance wind energy does, and new installed capacity continues at great pace across the globe, but especially in the global north. Indeed, the Ember Global Electricity Review 2024 notes that in 2023, solar was the source with the largest year-on-year percentage growth for the 19th year running. It is deployed swiftly, in a highly commoditized, highly scalable manner, from balcony solar plugged directly into a home to gigawatt-scale energy parks, all underpinned by its extreme modularity and the experience curve, concepts explained succinctly by Ben Fleischberg in his book How Big Things Get Done. Thus, solar is critical to decarbonising our economies, as it does the cheap and fast bit very well indeed. And these authors are huge fans. However, there are important tactical and strategic reasons why all renewable eggs cannot be put in the solar basket. First, security of supply of technology. The US is in the process of being replaced by China as the world's most powerful global nation and economy. China manufactures 2/3 of all the world's solar panels, and 8 of the top 10 manufacturing companies are Chinese. No one ought to have any quibbles with this. According to Rystad Energy, global manufacturing capacity of solar panels will double from 1,000 gigawatts in 2023 to 2,000 gigawatts in 2026, 80% of which would be in China. However, the US has been the world's most powerful economy for 120 years, and it looks at the upstart China with severe disapproval. Already in purchasing power parity, PPP terms, the Chinese economy is bigger than the US, and future growth prospects are a good deal higher in China. In his book, The Thucydides Trap, Graham Allison charts the history of war between the once dominant power and the upcoming one. We see lots of evidence that points in the direction of this power struggle currently. We, in Europe, will not wage war on China, but we could easily become collateral damage in the titanic struggle between the two majors. The favoured non-war weapon deployed by the US is sanctions. Sanctions could be applied to solar panels, and as Europe lies in the US sphere of influence, we could find ourselves unable to purchase Chinese panels. Second, locational suitability. Many areas of the world have weak solar irradiation, with very low capacity factors. In snowy areas, solar panels get blinded, which reduces their capacity to generate. Third, and most importantly, the gaps in solar supply. Solar is uniquely badly positioned to meet the main daily peak in electricity demand. This peak occurs when the sun goes down because the sun goes down. This becomes extreme during winter months at high and low latitudes. Batteries can and are being used to help cope with peak demand, but using batteries to shift supply between seasons is not possible. On the other hand, in Europe, as in many regions, when a large enough area can be considered, there is excellent complementarity between the generation of wind and solar, both over 24 hours and across 4 seasons of the year. Figure 7 shows how wind and solar form a near-ideal generation pairing. The optimal is always a mix. Given the economics of solar and increasingly battery storage, many experts suggest that solar and storage capacity growth to address summer demand will happen anyway. But in Europe, given the significant portion of our power consumption in the winter and our abundant wind resource, BNEF solar expert Jenny Chase emphasises there is no way we can build enough battery to shift energy from summer to winter. With 20 years' experience in analysing solar globally for Bloomberg New Energy Finance, Chase is widely regarded as an expert in all things solar generation and storage. Yet increasingly she has been vocal about the need for wind and policy support for wind as more solar is deployed. I think we should prioritise wind in Northern Europe because wind blows at night and in the winter. Building wind would put us on a much better pathway to get to actual net zero than building a load of solar and hoping. It is probably something that should be a consideration in energy policy, because the thing is, if you've got solar causing very low power prices all summer, and in spring, and in autumn especially, then wind farms, for example, don't get built because they're not making enough money over the year. And if they don't get built, they're not running in the winter. So I do think that right now, particularly in places like Europe, which is quite far north, incentives and policy drivers for wind should be a higher priority than drivers for solar. Wind and solar are variable and intermittent in output, respectively. It is this that marks the second great difference between fossils and renewables. Fossil-fired generation can be adjusted to customer demand, whereas wind and solar energy, being climate and geography-based systems, must be harvested when and where the wind is blowing or the sun is shining. There are therefore 3 large problems to be solved in the transition from fossil use to renewables. Planners of the transition have to answer these questions. Question 1. Where can the wind and solar be harvested for maximum effect? i.e., where does the wind blow strongest, and where is the solar radiation at its most intense? Question 2. How are we to compensate for the variability and intermittency of renewable sources of energy? Question 3. How is energy to be transported from remote areas where the basic energy can be harvested at lowest cost to the places where it is needed by the customer? There is an ancillary question. which is of practical importance but more easily soluble. How will the new generation and transmission arrangements fit into the existing transmission and distribution system? Question 1. Where can the wind and solar be harvested for maximum effect, i.e., where does the wind blow strongest, and where is the solar radiation at its most intense? Renewable energy systems are climate and geography based. Both of these parameters are interdependent. To a lesser extent, they depend on population distribution and the acceptability of wind and solar installations in heavily populated areas. Europe is heavily populated, with generally low wind speeds on land. It is cheaper to build on land, but community resistance to wind, in particular, can reach levels where it becomes particularly difficult. A public procurement tender, or auction, is a process run by a national agency to incentivise needed renewable energy development in a competitive way. The structures and mechanisms vary from country to country, but the principle is the same. The company who can deliver power earliest, cheapest, and satisfying other criteria like using local suppliers gets a contract to do so. The simplest metric to evaluate and award is the committed price, in euro per kilowatt hour, at which the project will deliver power to the grid. In public onshore wind auctions in Germany in recent years, not all the potential contracts were awarded, despite higher contract prices. Typical contracts were German offshore wind tender, July 2024. Tendered capacity, 2,700 megawatts. Permissible max value, €0.0735 per kilowatt hour. 197 bids, totaling 2,400 megawatts. Contracts were awarded to 2,300 megawatts. Bid values, €0.072 per kilowatt hour to €0.0735 per kilowatt hour. Average volume weighted bid value, €0.073 per kilowatt hour. German offshore wind tender, March 2024. Tendered capacity, 2,486 megawatts. Permissible max value, €0.073 per kilowatt hour. 129 bids, totaling 1,981 megawatts. Contracts were awarded to 1,836 megawatts. Bid values, €0.0725 per kilowatt hour to €0.0735 per kilowatt hour. Average volume weighted bid value, €0.0734 per kilowatt hour. German onshore wind tender, 1st of September 2022. Tendered capacity, 1,320 megawatts. Permissible max value, €0.0588 per kilowatt hour. 87 bids, totaling 772 megawatts. Contracts were awarded to all submitted bids. Bid values, €0.0576 per kilowatt hour to €0.0588 per kilowatt hour. Average volume weighted bid value, €0.0585 per kilowatt hour. German onshore wind tender, 1st of February 2021. Tendered capacity, 1,500 megawatts of onshore wind. Permissible max value, €0.06 per kilowatt hour. 91 bids, totaling 718 megawatts. Contracts were awarded to 89 bids, with a volume of 691 megawatts. Bid values, €0.0515 per kilowatt hour to €0.060 per kilowatt hour. Average volume weighted bid value, €0.060 per kilowatt hour. With Denmark's tender for the 5th of July 2021, no bids were received, as developers preferred to establish projects on market terms. In 2022, the Danish Energy Agency announced that it did not expect a need for further subsidies for onshore wind. Despite the competitiveness of new wind turbines, few onshore turbines are installed. Excluding test models, Denmark only installed one onshore wind turbine, 3.6 megawatts, in 2023 due to planning and grid constraints. At European level, onshore wind installations have stabilised, around 15 gigawatts annually since 2017. The continent on 3 sides is surrounded by seas, including the North Atlantic. The farther north one goes, the more energetic are the winds. Off the coasts of Ireland, Scotland and Norway, capacity factors, driven by very high wind speeds, 11 or 12 metres per second, reach 65%. The maps in Figure 3 and Figure 4 show where the resources are in Europe. In Europe, complete decarbonisation indicates that something in the order of 740 gigawatts of wind capacity has to be built offshore, 450 gigawatts onshore, as well as 1,000 gigawatts of solar PV. Calculations leading to these estimations are expanded later in Chapter 8. Recent figures from ENTSO-E suggest those figures may be even higher. Indeed, in one of its decarbonised scenarios published in 2024, ENTSO-E suggests that more than 2,193 gigawatts of solar would be needed to decarbonise Europe. For the purpose of simplicity, throughout this second edition, we have referred to the more conservative original estimates, but note that fulsome modelling with updated assumptions will be a material first step towards delivering the proposals in this book. The situation is different in the US and China. In the US, the high mesas stretching from North Dakota to the Gulf of Mexico have wind speeds of 9 metres per second and capacity factors of 40 to 45%. There are very low populations in these states, and so far no objections have been encountered to erecting turbines there. In China, Inner Mongolia is at an elevation of 1,600 metres. This huge area, 1.2 million kilometres squared, or 13 times the size of the island of Ireland, could be the home of millions of megawatts. Apart from Europe, most states with a shoreline will develop offshore wind, some faster than others, including California, Japan, China, South Korea, Taiwan, and many, many more. Question 2. How are we to compensate for the variability and intermittency of renewable sources of energy? This is a key question, with a number of possible and complementary solutions. The first strategy that can be adopted will result from a study of the wind in any particular area. Different ways of coping with wind variability can be devised when one has knowledge of what causes the wind to blow. Winds in Europe, and in most of the US, are storm or pressure driven. In Europe, storms usually arrive from the North Atlantic, moving from southwest to northeast. What happens at present is that there is a peak of generation, driven by the high wind speeds in a storm in Ireland, followed by a peak in the UK, and so on to Belgium, Holland, Denmark, etc. There is very little electrical interconnection between these countries, and that leads to peaking, as well as significant curtailment of wind generation. In Ireland, the dispatch down was 10.7% of available wind generation and 9.1% of solar in 2023, increasing to 11.3% for wind by mid-2024. 33 terawatt-hours were lost due to curtailment in Germany during 2022 and 2023, at a cost of €7.3 billion. The 19 terawatt-hours curtailed in 2023 was equal to 4% of total German electricity generation. Imagine if a situation existed where there was a profound interconnection between all European countries. Figure 5 shows what happens when a storm arrives at Ireland and travels across Europe. If there were profound interconnection between European countries, and there was a very large quantity of wind generation captured in the storm's initial attack off the west coast of Ireland, the generation profile shown in Figure 6 is the conceptual representation of what would happen. With the existing interconnection, the generation profile in blue is what happens. The red line shows the generation profile that would follow from profound interconnection across Europe. Clearly, the variability of the energy is greatly reduced. Also, more energy is captured from the storm on account of the location of sea-based generation off Ireland. As interconnection increases, by way of a meshed offshore grid, curtailment costs and variability of wind energy reduce. Therefore, the amount of electricity storage that has to be built to counteract variability reduces. What we have just described is one method of dealing with variability. This is a short-term, duration of the storm, way of mitigating wind energy variability. Are there any longer-term ways of reducing variability? Again, there is a reduction in variability over the course of a year arising from profound interconnection. The previously mentioned graphs showed broadly east-west interconnection. Profound north-south interconnection would have a dual effect in the following ways. 1. Wind around the southern Mediterranean basin follows a different pattern to the storm-driven northern wind profile. This, by itself, would reduce variability if the two areas were interconnected. Heat-driven wind around the Mediterranean is uncorrelated with pressure-driven wind in the north. This leads to a portfolio effect which reduces variability. 2. There will be a major amount of solar energy to be harvested around the Mediterranean. During the summer, when wind power in northern Europe is weak, solar generation around the Mediterranean is at its strongest. With profound interconnection, this strong solar contribution would contribute to reduced variability. The opposite effect would happen in winter, when generation is strong in northern Europe and weaker from solar around the Mediterranean. The complementarity of wind and solar is seen in Figure 7, which is based on data from the International Energy Agency, IEA. The IEA graph shows the complementarity of wind and solar across the seasons since 2010. With sufficient interconnection, wind and solar almost balance one another. Such interconnection refers to the north-south sections of the supergrid. The first major strategy to deal with variability is to build a Europe-wide meshed grid. We call this the supergrid. The second strategy is to have storage devices installed in each nation-state. The amount of storage needed is, of course, greatly reduced by the existence of the supergrid. Storage is still expensive, although reducing in price year on year. A major contribution to the storage issue could technically come in the form of all the car and lorry batteries. As we pointed out above, it is Europe's and every nation's goal to be rid of fossil-fired road transport. There is a total fleet of roughly 300 million vehicles in Europe. If they were electrified, they would have a storage capacity of approximately 100 kilowatt-hours each. If they were kept fully charged, there would be 30 terawatt-hours of electricity storage in the fleet. Of course, it is highly unlikely that they would all be kept fully charged, so 30 terawatt-hours is a theoretical maximum figure. When parked, much of the fleet could be connected to the grid via interactive connections. Up to now, connections to the grid have been used almost exclusively for charging vehicles. There is nothing to prevent a two-way flow of electricity, vehicle to grid. Shortages of supply from wind and solar could be alleviated by drawing on the vast amount of stored energy in the fleet of vehicles connected to the grid when parked. A great many people drive to work and park the car until it is used to drive home again. Not all of the fleet would be connected to the grid at any one time, and the grid would not have access to all of the stored electricity. The quantity of electricity to which the grid would have access could be set by the vehicle owner. If their battery were, for example, 80% full, they might decide to allow the grid access to 50%. This would mean they would have 30% left to drive home, or wherever. There would be a compensating payment for the use of this electricity, which could be paid out as cash or netted off against electricity payments. Already today, in some markets, EV charging patterns are linked to the hourly market price of electricity, so that charging happens at the lowest cost during hours of relative abundance of electricity. In Figure 8, the amount of stored electricity in the batteries of cars is plotted against the percentage of cars connected to the European grids. 3 scenarios are looked at, where 50% of vehicles are connected to the grid, where 40% are connected, and where 30% are connected. As indicated in Figure 8, drivers would be enabled to set the amount of electricity which the grid could access. The graph shows the quantities that would be available if, on aggregate, the drivers set numbers from 50% to 5%. The 2019 average cost of utility-scale battery electricity storage systems, BESS, was $341 per kilowatt-hour. BESS are large batteries storing and supplying electricity from chemical-based battery technology to the grid, over a range of time from a few minutes to several hours, such as lithium iron phosphate. This would be something like a few million phone batteries connected to the grid. Figure 9 shows the amount of investment that would not have to be made in utility-grade battery storage. Specifically, the graph shows the investment foregone as a function of the amount of energy in terawatt-hours in electric vehicle batteries to which the European grids have access. If 10 terawatt-hours of BESS was the contribution made by vehicles, there would be a saving in capital expenditure, CapEx, in the order of $2,000 billion, or $2 trillion. This means that the public electricity service would not have to invest in the battery storage already paid for by the vehicle owner. Even at 0.5 terawatt-hours vehicle battery storage, there would be a saving of $199 billion. This analysis was done based on 2019 studies, and battery prices have dropped substantially since then. The value proposition is still directionally correct. Hundreds of billions to trillions of potential savings of money for utilities, and the likelihood of electric vehicles being rolled out faster has increased. Vehicle drivers could be encouraged by incentivizing them to make more electricity available. The driver's investment is already made by virtue of buying the car. It is sunk cost, which reduces the amount of utility battery storage that has to be invested in by the public electricity utility. So the effect of vehicle battery storage is to reduce the cost of electricity. Batteries as part of vehicle propulsion systems are not paid for by the electricity companies. And to the extent they are used to meet situations where the renewable generation is less than demand, they contribute to more reliable and cheaper electricity for the populations. At the time of writing, innovative market disruptor Octopus Energy UK is trialling this vehicle-to-grid prosumer proposition with the Octopus Power Loop. There may be times when weak sunshine, combined with lower wind speeds and weak hydro inflows, is the case across Europe. Batteries may not be able to compensate for the shortfall in supply. In this instance, demand-side management is the solution. What happens here is that certain types of demand can be extinguished with barely noticeable loss of service to the customer. This reduction in demand to match supply is made possible using smart meters and smart appliances. These are backed up by minute-to-minute knowledge of the quantity of available electricity. When supply and demand are known, the price of electricity can be determined. At certain price points, various classes of appliance can be automatically switched out. Freezers can have their electricity cut off and persist with keeping food frozen so long as they are opened very infrequently. A warning light on the appliance, fueled by a tiny rechargeable battery, tells the freezer owner that electricity is temporarily cut off. Heating of buildings can be reduced by 1 degree Celsius with little noticeable difference to occupants. This quenching of load depends on a continent-wide system of communications, so that every country can be treated the same and bear their share of the temporary loss of supply burden. Smart metering technology exists today, although, in general, appliances are not fitted with it. In an electrically powered society of the future, it would be a trivial exercise to have all appliances fitted with smart connectors to the grid, which respond to dynamic pricing. EU regulation on smart metering has been in place since 2009. A study by ACER, the EU Agency for the Cooperation of Energy Regulators, found that 54% of European households had an electricity smart meter at the end of 2021, while in 13 EU countries, the penetration rate was over 80% at the end of 2022. By 2030, 266 million smart meters would be installed in Europe, corresponding to 92% of households. A European Commission study estimates that the average cost of installing a smart meter in the EU is between €180 to €200, while on average each meter would provide savings of €230 for gas and €270 for electricity per metering point, and save between 2% and 10% of energy. The authors note that at the time of writing in August 2024, dynamic pricing is still not available in every European market, despite regulations brought into place in 2022. All of this indicates that a focus on facilitating rollout of the intelligent market instruments is worth prioritising for near-term impact. Not only will it avoid unnecessary capex investment, as illustrated above, but also by avoiding the associated utility-scale project build-out, the related permitting and social licensing, therefore additional schedule considerations are also avoided. If car owners are appropriately incentivised and facilitated, storage and grid services could be partly socialised. From a behavioural science perspective, the added benefit of this is to provide an opportunity for citizens to engage meaningfully in a collective action, which, when supported, demonstrated, and promoted correctly, may lead to a virtuous cycle and wider behavioural change. This ultimately could result, e.g., in helping to shift discretionary consumption during peak demand hours, or adapt discretionary consumption to dynamic pricing signals, further reducing the total system requirements in terms of investment and resourcing to support build-out. Question 3. How is energy to be transported from remote areas where the basic energy can be harvested at lowest cost to the places where it is needed by the customer? The urgency for Europe to develop its continental transmission system can be grasped when it is observed just how profoundly China has set about sustainably powering its economy. See figures 10 and 11. Chinese endeavours should be seen in the context of accomplishing two major feats: having a completely sustainable carbon-free energy system by 2060 and continuing with its strong economic growth during this transition. We have outlined how the grid can become a variability reducer. In the next chapter, we describe the grid of the future. This is the supergrid. Chapter key points. 1. Wind and solar generation are weather dependent, and so are variable and intermittent. 2. Solar and wind are highly complementary. Solar as a generation source is not enough in the darker months, even with enormous battery deployment. Wind is critical to achieve fully clean, secure, affordable energy, and is strong throughout the winter. 3. The wind is always blowing somewhere. When all the somewheres are linked up through a large enough grid, smooth power output will result. 4. Much wind-generated electricity in Europe is remote from the customer, as it is sea-based. 5. The richest solar resources are to be had around the Mediterranean basin. 6. Connecting wind and solar generation reduces the variability and intermittency of both. 7. The supergrid joins up these remote renewables, smooths their output, and transports the power to the customer. 8. Using batteries, whose costs have fallen by over 90% in the last 15 years, the inadequacies of renewables are further reduced. But since we cannot build enough battery to shift energy from summer to winter, wind remains critical. 9. Some battery capacity could come from electric vehicles. 300 million electricity-powered vehicles in Europe could be connected to the grids when parked, allowing the electricity utilities access to their stored energy. 10. This vehicle-to-grid arrangement would reduce the total capital requirement to install utility-scale batteries, and the electricity utilities who benefit could offer a reduced price of electricity for consumers. Octopus Energy UK is currently trialling this with the Octopus Power Loop.